Right. All right, it's great to see you all back. Welcome to another session of CE 397, Control Theory for Smart Infrastructure. Let's quickly recap what we talked about last time. So last time we started our journey into the deep and dark forests of linear algebra. We talked about a couple kind of abstract concepts. In particular, we wanted to kind of initiate our discussion of vector spaces. So let's just quickly recap from last time a couple of different terms. So we talked about fields, we talked about vector spaces, and we talked about subspaces. What, in your words, is a field? Or what are some examples of fields? Sorry? Sorry? Any examples of fields? Yeah. So that's probably the most familiar example of a field is the real numbers with conventional addition, conventional multiplication. Okay. So just kind of in your own words, what are fields? What is it a field of, or what did we call it a field of? Yeah, so a field, it consists of essentially a set of scalars along with an operation that we call addition and operation that we call multiplication. And we also had some constraints in that, both addition and multiplication, we had to have an identity element and an inverse for each of those operations. So these are fields consist of scalars along with addition and multiplication. Okay, and this addition and multiplication operation might be slightly different than the conventional description of addition or multiplication that you may be familiar with. Okay, so we talked about fields, then we talked about vector spaces. So this is kind of the main topic of last lectures. So what, in your own words, is a vector space, or what's kind of the general idea of a vector space?
A set of vectors such that we have operators that you can add scalars and you can scale.
Yes. Yeah, so it's a set of vectors along with two operations, vector addition and scalar multiplication. So you can have these vectors that are in your vector space, you can scale them, you can add them together. And when you do that, you end up with other vectors that lie within your vector space. So we say that it is, our vector space is closed under scalar multiplication and vector addition. So set of vectors that we can scale by scalars in our field and add together. And what are some examples of vector spaces that we talked about? The real number line. So real number line along with just conventional addition and multiplication. What's one more example of a vector space that we talked about? Polynomials. Okay, so we might call those, let's see, how do I usually denote polynomials here? So there's a specific notation we use. It'll be something of the form R4 of S if your polynomial is in S. And then you'd usually denote that the fields that you're applying the coefficients over. Okay, so polynomials are also vector spaces. Okay, so very good. And then the last thing we talked about were subspaces. So kind of in your own words, what is a subspace of a vector space? What is a subspace of a vector space? So let's say we have a vector space that's just R3, so 3D space. What would a subspace of R3 be? An example of a subspace. R2? Yep, so R2 is a subspace of R3. And also R1, yeah, yep. So those are both subspaces of R3. So it is a subset of a vector space that is also a vector space itself. Meaning that it's closed under what two operations? Yeah, so vector addition, scalar multiplication. Very good. So out of all of the definitions that we gave last time, this is kind of the intuitive understanding that I want you to get. So we define fields, we have vector spaces, and we have subspaces, and they all have relatively intuitive definitions. And as we go through more examples of these concepts, I think they'll become more clear. Are there any questions on these general concepts before I move on?
The subspace is like for a vector space like of lower
It will have dimension less than or equal to the vector space that it is a subspace of. So for any vector space, the vector space itself is also a subspace of itself. So if you have a vector space V, V is a subspace of V. Yeah. And also the zero vector is a subspace of any vector space. Great question. Are there any more questions on these general concepts before I move on? Okay, so today we are going to finish up our discussion of vector spaces. We're going to talk about three more concepts. We're going to talk about span, linear independence, and we're going to talk about bases. Okay, so who's familiar with at least one of these terms? Okay, one of these terms? Okay. Great, so we're going to talk about span, linear independence, and bases, and then we're going to cover some more concepts that are going to help us characterize vectors. We're going to talk about norms, inner products, and orthogonality. We're going to review some concepts that you may have seen in undergrad and extend them kind of as we have extended our definition of vectors. So too are we going to expand our definitions of things like norms and inner products. Okay, great. Well, with that, the first concept I want to talk about today is linear independence. Okay, so who here is familiar with the concept of linearly dependent and linearly independent vectors? Okay, so it's just one. So it's a fairly intuitive concept, and you've probably seen it in some form before, but it's a very important concept going forward. So let's say we have, let V be a vector space, or sorry, let V be a non-empty collection of vectors. So we have some set of vectors, V1, V2, V3, all the way through something. So this is a non-empty collection of vectors. Okay. In some vector space, which I will just call U, because it's hard to differentiate between different fonts here. So V is just a collection of vectors. It's not necessarily a vector space itself. U is a vector space. So we can define two concepts. The first is linear dependence. Okay, so we say that V is a linearly dependent set of vectors. If and only if there exists some collection of k distinct elements of V and a set of scalars, not all zero, such that if you scale each vector by your scalars and add them up together, you can get the zero vector. Okay, so V is a linearly dependent set of vectors if there exists k distinct elements, which I will call V1 through Vk in V, and scalars alpha 1 through alpha k, not all zero. Such that if you scale your elements, so if you take alpha 1 times V1 plus alpha 2 times V2 all the way through alpha k times Vk, you can add them up to get the zero vector. Okay, so we go through an example of this concept. So this is for a linearly dependent set of vectors. Let me go through an example of a linearly dependent set of vectors. Okay, let's say we have two vectors in R2. So we'll have 2, 2, and we have 1, 1. Okay, so we have a set of two vectors. We can come up with scaling coefficients alpha such that we can add these two together and get the zero vector. So what are two coefficients we can scale these by and add them together such that we get the zero vector? Yeah, so we could add 1 times 2, 2 plus -2, 1, 1, right? So because we can find coefficients, not all zero, such that when we scale them and add them together and produce the zero vector, this means that these two are linearly dependent. Okay. So in the context of 2D space, this would mean that your vectors are collinear. Right. So analogously, we have linear independence. Okay. So we say that V is a linearly independent set of vectors. If and only if for any collection of k distinct elements of V, okay, so if we have, V1 through Vk, and for any scalars, alpha 1 through alpha k, and we have that if we scale those elements of V and add them together and get the zero vector, so if we take our elements of V, add them up, and get the zero vector, it implies that all of those alphas must be zero. Right. So for a vector, for a collection of vectors to be linearly independent, if you are able to scale those vectors and add them up together to get the zero vector, it implies that all of your coefficients alpha have to be zero. In other words, there's no way to scale those vectors together and add them together to get the zero vector unless all of your scaling coefficients are zero. Okay, so let me give you a quick example of a set of linearly independent vectors in R2. So let's say we have 1, 1 and 0, 1. Is there any way to scale these vectors and add them together to get the zero vector? Well, there is actually. What would that be? Right, if your scaling coefficients are 0 and 0. So because the only set of scaling coefficients that give you the zero vector is 0 and 0, these two vectors are linearly independent. Okay, are there any questions on linear independence versus dependence so far? Okay, who's seen this concept before in a different setting? Is this something they taught you in undergrad linear algebra? Yeah. Okay, cool. So let me give kind of a more intuitive description of linear independence versus dependence. So let's say we have two planes here. I'm just going to draw two plots. Trying to make them evenly sized here. Oh no. There's kind of a hidden space over there that I can't draw. Okay. All right, there we go. Okay, so first let me draw a set of linearly dependent vectors. So the following set of vectors is linearly dependent. Let's say we have V1 and V2. We just label our axes here. It's x1, x2. Okay, so these two vectors are linearly dependent. If you're looking in R2, basically for two vectors to be linearly dependent, they have to be collinear with each other. Okay, so you can take V2, scale it by some negative amount and add it to V1, and you will get the zero vector, right? Linearly independent vectors in R2 are basically everything else. Okay, so everything that is not collinear would be a set of linearly independent vectors in R2. Okay, so this set of vectors, for example, would be linearly independent. So again, this is linearly independent. And this is linearly dependent. Okay, so it seems like a simple concept, but it's going to be very important for our discussions later on. Okay, are there any remaining questions about linearly dependent vectors versus linearly independent vectors? All right, so it's fairly intuitive. Okay, so let's move on to talk about span. Who's familiar with the term span in linear algebra? A little bit? Okay, so let me give you the formal definition of span. The span of a set of vectors is essentially the collection of vectors that you can reach by scaling those vectors and adding them together. Okay, so that's the intuitive definition. Here's the formal definition. Given some set of vectors, which I'll call V, the span of V is the set of all finite linear combinations it's the set of all finite linear combination of the vectors in V. Okay, so we can write it as, I'll often write it like this. I'll write SP. Okay, so I'll say SP of V, the span of V, is equal to the set of vectors V, where V are equal to alpha 1 V1 plus alpha 2 V2. Underline these here. And so on, all the way to alpha K VK. And this is for AI in our field F and VI in our vector set V for all K and the natural numbers. Okay, so let's go back So again, intuitively, the span of a set of vectors is just all the vectors that you can reach by scaling those vectors by some amount and adding them together. Okay. So naturally, the span will in general be an infinite set of vectors, right? It's all the vectors that you can reach by scaling and adding your vector set together. So let's go back and let's look at these two examples in R2. And let's think about what the span of each of these cases is. So what is the span of V1 and V2 for this case? Right. It's the line that these vectors lie on. Okay, so in both the positive and negative direction. Okay, so this is the span of V1 and V2. And let me just keep it consistent and underline these here. All right. So the span of V1 and V2 is this line through the origin. It extends outward infinitely in each direction. What is the span of this two set of vectors here? Right. So the span of V1 and V2 here is all of R2. Why is that? Right. So we can take these vectors V1 and V2. If we scale them together, we can reach any point in the plane by adding them together. So for instance, if you took V2 here and you scaled V1 and you added it to V2, you might end up running out of colors. You might end up somewhere over here. Then you can scale V1 by a little bit more. You'll end up somewhere over here. You can scale V1 by a little bit more, end up over here. You can take V1, you scale it by a negative amount, end up over here. Scale it a little more, end up here. And then you can take V2, scale it a bit more, add V1, you end up over here, and so on. So you can reach every point in the plane by scaling these two vectors and adding them together. So the span of V1 and V2 is equal to R2. Great. Are there any questions on span before I move on? Well, who's encountered the concept of span before in linear algebra? Just to check. Okay. So it's often kind of the more abstract concepts in algebra. Linear algebra aren't taught at the undergraduate level, but I want to make sure these are clear. They're not particularly complicated concepts, but it's important to start getting these ideas in your mind. Okay. So the final topic I want to talk about before we move on to the concepts of norms, inner products, and orthogonality. The final concept I want to talk about are bases. So who's heard of a basis for a vector space before? Okay. So let me give you the formal definition for a basis. So a basis of a vector space V is a subset of V. So it's a subset B of V, which is linearly independent so it's a linearly independent set that spans V. Okay, so what does this mean? What is a basis? So a basis is essentially a collection of vectors in your vector space that is linearly independent and that spans V. So in other words, you can take your basis. So you have a basis which consists of some collection of vectors that lie in V. you can scale those vectors by some set of scalars and add them together and reach any point in your vector space V. Okay, so it provides a way of reconstructing any vector in your vector space by scaling them and adding them together. Okay, so note that a basis here refers to an actual finite collection of vectors and not a vector space itself. Okay, so we're talking about a basis from which we can reconstruct any vector in the vector space. All right. And I'll go through some examples. So let me just go through a quick example, actually, really quick. Let's say we have R2. So our vector space is equal to R2. So what is a basis for R2? Right. So that would be what's called the canonical basis. Is this basis unique? No. So according to our definition, they don't need to be orthogonal. They just need to be linearly independent. So another basis might be 1, 1, 0, 1. These we know are linearly independent, and we also know that they can span V. So we can scale these and add them together to get any vector in R2. Okay, so those are two examples of bases. So again, they don't need to be orthogonal. They just need to be linearly independent for it to qualify as a basis. Right, so very good. The final definition I want to give you is the dimension. So we talked a bit about the dimension when we first got into linear algebra, but formally, the dimension of a vector space V, we will denote by dim of V, is the number of elements in any of its bases. So it's the number of elements in any of its bases. Okay, so for example, if we want to know what the dimension of R2 is, so we know that it's going to be 2 because it's called R2, but we simply just count the number of elements that are in any of its bases. Okay, so in this case, we have 2 basis elements, therefore the dimension of this vector space is 2, which we already knew, but that is the formal definition of dimension. Yes.
But then, so the basis also needs to be defined as like the least number of vectors. Because even if I had 3 vectors in the basis, I can span the whole space.
Right. So this follows from our definition of linear independence.
Oh, I see.
Right. So for our collection to be said to be linearly independent, they all have to be linearly independent. Yes. Yeah, a good question. All right. So let's go through an example of representing vectors in different kinds of bases, just to help make clear what I mean. So let's consider the following 2 bases for R4. So I'll say, consider the following 2 bases for R4. The first is going to be the standard basis or the canonical basis. And this will be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Oh, sorry. 0, 0, 1, 0. I sound like a computer. And 0, 0, 0, 1. Okay, there we go. Okay, so that's our standard basis. It's the one that we are most familiar with. It's the one we are used to working with. Let's define an alternative basis for R4 that actually is useful in some cases. Who's heard of wavelets before? Okay, so we're going to define a new basis, which I will call the Haar wavelet basis. So this is a real thing that is used in signal processing. So we're going to define a new basis where our basis elements are 1, 1, 1, 1, 1, 1, negative 1, negative 1, 1, negative 1, 0, 0, and 0, 0, 1, negative 1. And you can verify that this is a basis. All of these vectors are linearly independent and they span R4. Okay, so you can reach any vector in R4 by scaling these and adding them together. Okay, so let's say we want to represent a vector in each of these bases. So let's say we want to represent the vector x, which I will call 3, 3, 1, 1 in the standard basis. So note that anytime we are writing a vector, we have to specify which basis we're talking about. So this is the vector 3, 3, 1, 1 in the standard basis. Okay, so in the standard basis, we can write this vector as follows. Okay, so we have 3, 3, 1, 1. So we want to create this vector by taking our standard basis, scaling it by some amount, and then adding those elements together. And 0, 0, 0, 1. Okay, so it's pretty clear what the coefficients need to be. So what does the coefficient of the first one need to be? 3. The second one is 3. Third one is 1. The fourth one is 1. Okay, so we can alternatively write this as follows. We write our basis stacked together on the left-hand side, which will be the identity matrix. So all I've done here is I've taken our basis, I've stacked it into a matrix, multiplied by the coordinates in that basis. So we have 3, 3, 1, 1. Remember that this follows from the second definition I gave to you for matrix vector multiplication. Remember that this matrix vector product is equal to the first column of A times the first element of the vector, plus the second column of A times the second element of the vector, and so on. Okay, so when we're talking about any vector, we have to be careful that we're talking about that vector in some basis. Okay, and by default, that will be the standard basis. So let's go now and let's express this in our Haar wavelet basis. Okay, so let's say we have our vector 3, 3, 1, 1 is equal to some coefficient alpha 1 times our first basis element, which was the vector of all ones, plus some second basis element times 1, 1, negative 1, negative 1, plus some third basis element, which is 1, negative 1, 0, 0, plus our fourth basis element, which is 0, 0, 1, negative 1. Okay, so how can we represent this vector in our new basis? How can we add these up together to get our original vector in the standard basis? So I happen to pick a vector that has a sparse representation in the Haar wavelet basis. So we can get our vector 3, 3, 1, 1 as follows. So we take 2 times the first basis element plus 1 times the second basis element plus 0 times the other basis elements. Okay. And if we want to write that in the matrix vector product form, that means that actually, let me write it like this. We have that 3, 3, 1, 1 is equal to the matrix formed by our basis vectors. So that'll be 1, 1, 1, 1, 1, 1, negative 1, negative 1, 1, negative 1, 0, 0, 0, 0, 1, negative 1 times, what will our vector here be? Two, 1, 0, 0. Very good. Okay. And to make it explicit here, we express 3, 3, 1, 1 in the standard basis, which in this case, if we express it in matrix form, will be the identity matrix here. Okay, so we can express any vector in any basis for R4 as long as the vectors are linearly independent and they span R4. So looking at this, why might we want to use the Haar wavelet basis to represent this vector? So it turns out that sometimes, oh, yes?
I was just thinking it's the only 2 vectors represented.
Right. So often, specifically, if we're interested in signal processing, especially as it relates to dimensionality reduction, it's often helpful to pick a basis in which our signal is going to be or going to have a sparse representation. So in this case, we only need 2 basis vectors to represent this particular vector. So sometimes choosing your basis can make a particular problem more computationally tractable. Right. So, great. So that is a basis in R4. Let's see how much time we have. We have about 35 minutes left. All right. Let's see here. I'll give you another example very quickly, just to illustrate that this is not just for what we conventionally think of vectors. So let's say we're looking at the vector space of polynomials. This is something I think that you'll be looking at in a future homework. So we say that V, our vector space, is the vector space of polynomials of degree less than 4, or less than or equal to 4. So V we write as R4 of S, where S is our variable for our polynomial over the field of R. So the coefficients we're scaling S by are in R. Okay, so one basis. So one basis for this vector space is, we'll just write our basis elements as the letter E. So we have E1 is equal to S cubed. E2 is equal to S squared. E3 is equal to S, and E4 is equal to 1. We can also define another basis. So I'll call this one E bar of 1 is equal to S cubed minus S squared. E bar of 2 is equal to S squared minus S. E bar of 3 is equal to S minus 1. And E bar of 4 is equal to 1. Okay, so both of these are valid bases. You can represent any polynomial in S of degree less than or equal to 4 with either of these bases, and they will work. So in this case, let's consider the vector, which is a polynomial, which I'll call X, is equal to 3S cubed plus 2S squared plus, minus 2S plus 10. So we can write this out in either basis. So for the first basis, we just replace S with, these different terms here. So in the first basis, we have that x is equal to 3 times E1 plus 2 times E2 minus 2 times E3 plus 10 times E4, right? Because our basis elements are just s cubed, s squared, s, and 1. In second basis, we can also write this same polynomial as 3E1 bar plus 5E2 bar plus 3E3 bar plus 13E4 bar. So both of them are valid bases. Often in this class, I will write them with the basis elements on the left side and the coordinates on the right side. So for example, in this case, we would have that E1, E2, E3, E4 times 3, 2, negative 2, 10 is equal to E1 bar, E2 bar, E3 bar, E4 bar times what? What are our coordinates in this basis?
3, 5, 3.
Yes. So the coordinates are those coefficients that are applied to our basis elements. Okay. Great. So that is how you can represent a polynomial, which is a vector, in 2 different sets of bases. All right. Are there any questions on basis before I move on? I'll lay bases to rest for the rest of the lecture. We'll probably get back to it on Tuesday when we start talking about linear transformations and what they really mean. Any questions on these 2 examples? All right, cool. Well, let's go ahead and move on. For the rest of lecture today, we're going to talk about a couple different concepts related to characterizing vectors and vector spaces. In particular, we need a couple different concepts to characterize the size of vectors and their orientation to one another. So these are going to be important concepts for the upcoming lectures in linear algebra. But we're going to talk about inner products, norms, and orthogonality. So who's familiar with the concept of a norm? Is anyone familiar with the concept of a norm in linear algebra?
It's like the length or magnitude of a vector.
Yeah, so it's a way of characterizing the magnitude, in some sense, of a vector. So you've seen it in linear algebra. Who's seen the concept of a norm in optimization? Has anyone done any work in optimization where you do, for instance, what are called like L1 norm optimization or L2 norm?
Deep learning.
Deep learning, yep. So what does it mean? What's the difference between L1 norm, L2 norm? What do these terms mean?
Square roots are like just across them.
Yeah, so it turns out that there's various different ways that we can define what the size of a vector is. There's various different ways we can define it, but all of them have to obey basically the same rules in order for it to be a norm. So let's talk about what norms are, what defines a norm. And essentially, norms give us a consistent way of characterizing the size of vectors. So Jimmy mentioned probably what's the most familiar norm that you're used to working with, which is the Euclidean norm or the 2 norm, right? So if you have, let me quickly do an aside here. So Euclidean norm, this is also called the 2 norm or L2 norm. Let's say you have some vector, maybe the components are 3 and 4, right? So let's call this V. So I picked a nice example here, but the 2 norm of V, as you probably know from geometry, would be 3 squared plus 4 squared. So it's the hypotenuse of this triangle here, which will be square root of 25, which is 5. Right. So that's probably the most familiar norm you're used to working with. This is not the only norm for the R2 vector space. There's other norms that we can define that are often useful for different kinds of problems, as I mentioned. Okay, so formally, a norm is a norm on a vector space. A norm on a vector space V over our fields, which I'll just call the complex numbers for generality here, but it could also be R. A norm is a mapping, which I'll denote by these double pipe characters here. So it's a mapping from the elements of our vector space V to the real numbers, such that the following properties hold. Okay, so there's 4 basic properties that a norm has to obey for it to be a norm. The first is what's called positive definiteness. Okay, so if you take some V from our vector space V and you apply our norm, it has to be greater than or equal to 0 for all V in our vector space V. On a related note, if our vector V's norm is equal to 0, this implies that V is the 0 vector. Okay, so our norm has to be positive definite. This is called positive definiteness. So we can't have a negative valued norm. And if the norm is equal to 0, that means that our vector has to be the 0 vector. Okay, the third property is the homogeneous property. So if we have our vector V from our vector space V, and we scale it by some amount alpha, and then we take the norm, this is equal to the absolute value of alpha times our vector, the norm of our vector V. Okay, and this is for all V in V, and for all alpha, alpha in real numbers. Okay, and this is called the homogeneous property. Okay, and the final requirement for a norm is that if you take 2 vectors and add them together, and then you take the norm, so let's say we have vectors u and v and we add them together and take the norm, this has to be less than or equal to the norm of our vector u plus the norm of our vector v. And this is called the triangle inequality. And if you'll notice, it's equivalent to the statement that and for the 2 norm, for example, that the hypotenuse of a triangle has to be less than its side lengths. Great. So those are the 4 properties that are required for a norm. So let's go through a couple of common examples of vector norms. The most common norm that you are familiar with is, as I mentioned, the 2 norm. Okay, so this is also known as the Euclidean norm or the L2 norm, but it is defined as follows. So let's say we have a vector x. We're taking the 2 norm. So to denote this, we'll usually have these double bars and then with 2 in the subscript. Okay, so the 2 norm of a vector x is equal to the square root of X Hermitian transpose times X. Okay, which is also equal to the square root of the sum of the elements from I equals 1 through n of xi squared. So note this is x in Cn. Okay, so it's equivalent to taking the inner product of a vector with itself and taking the square root. Okay, so this is the most common norm that you think of. This is how you would compute, for instance, if you're working in Euclidean geometry, this is how you would compute the length of a vector, right? Okay, so and I'll go through some examples of each of these norms applied to an example vector to make it more concrete. But a 2 norm is not the only norm. It's not the only valid norm. Another common norm is the 1 norm, as Huihai mentioned. Okay, so this is also called the Manhattan distance. Okay, the 2 norm is also called the Euclidean distance. And the 1 norm, if you have the 1 norm of some vector x, it's simply equal to the sum of the components of x, or the sum of the absolute value of the components of x from I equals 1 through n. Okay, so it's called the Manhattan distance because if you have, for instance, the distance between 2 points in a plane, so let's say you're trying to get from point A to point B, it would be the sum of the side lengths of those 2 components. So if you're taking a taxi in Manhattan, it's the distance that you would need to travel to get from point A to point B. Okay, so that is another common norm. You can generalize these types of norms into what's called the P norm. So this is a generalization of the 1 norm and the 2 norm, which we'll denote as X norm P. Okay, and this is basically just a generalization of the definition we had before. If we take the sum from I equals 1 through n of the absolute value of the elements in X raised to the P power, and then take the 1 over P power of that sum, that gives us the P norm of a vector. Okay, so it's just a generalization of the 1 and 2 norm to higher orders. Okay, and the final common norm that we deal with is called the infinity norm. Okay, so if we take this P norm and we take its limit as we go to infinity, what we get is what's called the infinity norm. This is probably, I would say, the 3rd most commonly used norm. It's used in a lot of nearest neighbor problems and stuff like that. It's simply equal to the maximum of the absolute values of the entries of X. Okay, so this is the max over I of the elements of X. And I'm going to go through an example really quickly, just to show you concretely for a vector in R2 what each of these norms looks like. Okay, so let's say we have a plane here. And let's say we have a vector. Actually, let me draw out some tick marks here. Okay, so we have a vector at -4, 3. So this side length here, this is -4. This side length here is 3. Let's take these different norms and see what they look like. Okay, so first of all, what is the 2 norm of this vector? 5, right? So this is a 3, 4, 5 triangle, so we already know what the answer is. But if we want to go through the computation, we take the square of this side plus the square of the horizontal side, add them together and take the square root. And that will give us 5. Okay, what is the one norm of this vector? Sorry? 7. Yep. So we take the absolute value of 3 plus the absolute value of 4 is equal to 7. So we just sum the side lengths together, sum the absolute values of the side lengths together. Okay, what about the infinity norm? Do you say 4? Sorry? Yeah. So the infinity norm is 4. So we take the maximum of the magnitudes of the side lengths, which in this case is 4. Okay, so that's conceptually what these different norms look like applied to a familiar vector in R2. So another interesting way to think about this, let's say we have a plane here in R2, a plane here in R2, and we want to characterize all of the vectors or kind of the locus of vectors that have unit norm in each one of these norms. So let's say we have 1, 1, -1, -1. What does the locus of vectors that have unit norm of 1 look like for the 2 norm? It'll be a circle, right? So for the 2 norm, all of these vectors around this circle have a norm of 2. And I'm not the best at drawing circles, but this is the vectors such that the 2 norm is equal to 1. All right, what about for the 1 norm? So we know that this one will be part of it, this one will be part of it, this one will be part of it, and this one will be part of it. Yeah, it'll just be diagonal lines here. Okay, so this is for the 1 norm equal to 1. Okay, and finally for the infinity norm, what's that going to look like? I think Aditya gave the answer. Yeah, it'll be a square. Yeah. So we have a square going like this. And sorry, I covered that up there. This is for infinity norm equal to 1. So this is the set of vectors such that the infinity norm is equal to 1. Okay, and for a given vector, generally the 1 norm will be the largest, the 2 norm will be smaller, and the smallest norm will generally be the infinity norm. All right, are there any questions on vector norms? Any question on vector norms before we move on? Who's seen these kind of different norms before? Okay, so this is a very important concept in optimization. As Huihai mentioned, often when you're trying to optimize an objective function, the norm that you choose for the optimization objective function matters a lot in terms of the outcome that you'll get. So one thing that you'll find, for example, is that the 1 norm is good at promoting sparsity in your solution. 1 norm is often used for a lot of machine learning applications, but the different norms kind of have different properties that'll affect what optimization you get out of that process. Okay, so very, very important concept to know. I quickly want to cover just a couple different matrix norms. So as I mentioned in the previous class, matrices can also be vectors in our definition of a vector space. So I want to go through a couple common matrix norms that you should just know for your graduate studies in general. There's 2 common matrix norms that I want to show you. The first is called the Frobenius norm. Okay, so kind of a funny name. So let's say we have A in R, well, It could be in C. A and C, m by n. Okay, the Frobenius norm of A is equal to essentially these, if you take all the elements of A, you take their absolute values and you square those and then sum them all together, that gives you the Frobenius norm. Okay, so it is equal to, if you take the square root, oh yeah, and sorry, you have to take the square root. So you have the sum over the rows and columns. So this is I equals 1, j equals 1 through mn of absolute value of aij squared. That is the Frobenius norm. And you can also show this is equal to the square root of the trace of A Hermitian transpose A. Okay, so that's an important identity. So again, as with vector norms, these are useful for characterizing the size of a matrix. So if you ever end up with a problem where you have to characterize what the size of a matrix is, you'll often use matrix norms to do so. So this is probably the most common matrix norm. The second most common is the matrix 2 norm. And the most intuitive definition for the matrix 2 norm is if you have a matrix and you take the quadratic product of that matrix with a unit norm vector, it's the largest value you can get. Okay, so when I say quadratic product, well, I'll show you what I mean right now. So let's say you have a matrix A, you're taking the matrix 2 norm. This is equal to the maximum of the square root of x, which is a vector, x Hermitian, a Hermitian, a x, where x has 2 norm equal to 1. Okay, so this expression inside here, this will become a scalar. Right? You're taking x Hermitian times a Hermitian a, all times x. That will produce a scalar. Essentially, you're trying to find, essentially, it's the maximum value you can produce from this product for a unit norm x. And as it turns out, as we'll show later in the course, this is equal to the largest eigenvalue of A for a square matrix, or the largest singular value of A for a non-square matrix. Did you have a question?
So why is this one called the 2 norm when the Frobenius one seems like they're kind of scaling up at the 2 norm?
Right. It's because we're applying the constraint that the vector x has to have a 2 norm of 1. So it's called it would be called usually the induced 2 norm on the matrix A. As for why it's called the 2 norm and this one is not, I don't exactly know. But these are the 2 most common matrix norms you'll see for characterizing what the size of a matrix is. The Frobenius norm actually turns out to be the sum of the squares of these singular values or eigenvalues of the matrix, and the matrix 2 norm turns out to be the largest eigenvalue or singular value of that matrix. So you've probably heard of eigenvalues before. Basically, singular values are that concept extended to non-square matrices. Okay. Great. And we'll talk about that when we get to eigenvalues a little bit later on. Okay, so I have a few more minutes here. What I'm going to do for the rest of the class, I'm going to cover inner products, and then I'm going to start talking about orthogonality. Great. So in the interest of time, let's move on. Okay, so let's talk about inner products. So we discussed briefly what an inner product is when we first started talking about linear algebra. And I kind of gave you just an informal definition of what an inner product is. As before, we can extend the definition of an inner product to talk about all these different types of vector spaces that we've been talking about. So for inner products, an inner product in general on a vector space V defined over a field, which I'll just call the complex numbers. You can also define it over R, is a mapping, which I'm going to denote by these little angular brackets here. So it's angular bracket dot dot angular bracket. It's a mapping to the complex numbers, satisfying the following properties. Okay, so just as before, we have to have 4 different properties for it to be a valid inner product. The first is that if you have 2 vectors, u and v, and you take their inner product, this has to be equal to the conjugate transpose of the inner product of v with u. This is for all u and v in our vector space. Note that if we're in the real numbers, this just means that they are symmetric, that the inner product of u with v is the same as the inner product of v with u. Okay. Great. The second property is called bilinearity. So it's not quite the same as linearity, but it's close. So if we have u and v in our vector space, and we take alpha u plus beta v, where alpha and beta are some scalars, and we take the inner product of that sum with another vector w, this is equal to alpha of the inner product of u with w plus beta times the inner product of v with w. Okay, and this is for all alpha beta in our field of complex numbers, and for all u, v, and w in our vector space, which is v. Okay, so this is called bilinearity. And then just as with norms, we also have positive definiteness. So if we have vectors v and we take the inner product with v, this has to be greater than or equal to 0 for all v and v. Okay, so the inner product of a vector with itself has to be greater than or equal to 0. And the fourth property, as you may guess, if you have a vector and you take the inner product with itself and it's equal to 0, that implies that v is the 0 vector. Okay, so that is positive definiteness. It's the same as for norms, right? Great. So those are the properties that need to be satisfied to have a valid inner product. Let's see how much time I have left. Okay, I got 4 minutes. Instead of moving on, I'm going to save orthogonality for next time. I guess what I want to do now is, are there any questions on any of the material that we've seen so far in class today? I know I've been going kind of fast because I'm trying to make up for lost time, but are there any questions on inner products or norms from our discussion today? Any questions? Okay. One thing I want to note is that for both norms and inner products, there are infinite dimensional versions. And this is the last thing I'm going to talk about today. So remember that I said that we can have infinite dimensional vector spaces. What that implies is that we can also have infinite dimensional norms, and these you will actually see later on when we get to our discussion of controllability and observability. But for the case of norms, first, let's say we just have let v be an infinite dimensional vector space. All right, so let's say our vector space V is equal to the vector space of continuous functions defined over the interval a to b. So these would be continuous functions of time over the interval a to b. You can verify that this is a valid vector space. And let x of t be a function that is in our vector space. So we can define a norm on this vector space. This essentially gives us a way of characterizing the size of a continuous function relative to other functions. So we can take the norm of x. Let's say we just want to look at the p norm of x. We can define that analogously as to the case of the vectors of complex numbers or real numbers. Essentially, all you have to do is take the integral from a to b of xt raised to the p power dt all to the power of 1 over p. So this is also a valid norm. So you can define norms for functions just like you can for vectors. This is analogous to the p norm for the case of a finite dimensioned vector. In the case of inner products, you can also define an inner product for an infinite dimensional vector. So let's say that we have, two functions. Let's say we have x of t and y of t. So you can also define the inner product of x with y analogously. So if it's in the real numbers, for example, you take the integral of a to b of xt, yt, dt. Okay, so we'll get to these types of infinite dimensional norms when we talk about the controllability and observability gramians a little bit later on. But the point I want to make is that you can define norms and inner products for functions as well as for finite dimension vectors. All right, well, with that, I will end the class. If you want any help on homework 4 before the due date or before the deadline at 11:59 p.m., just send me an email or a message on Canvas and I'll try to schedule a last minute session with you, or just come see me after class, okay? All right, thank you, and I will see you next week.